Hello, I'm Catie Kwan.
And I'm Jasmin Palmer.
Today we are presenting the paper Changes in Normal Force During Passive Dynamic Touch, Contact Mechanics and Perception by David Gueorguiev, Julien Lambert, Jean-Louis Thonnard, and Katherine J. Kuchenbecker. Humans perceive a combination of forces when they come into contact with their environment, as shown by the illustration on the right. The relationships between normal and tangential contact forces during manipulation have been well studied. However, not as much is understood about how the normal and tangential components of contact force are altered during dynamic exploration, and the effects of those changing components on human perception. Researchers at Max Planck Institute for Intelligent Systems and the Institute of Neuroscience at the Catholic University de Louvain in Brussels, Belgium, aim to study how humans perceive increases and decreases to applied normal force in natural and low friction conditions, and how normal force and tangential forces combine during haptic cues.
The relationship between normal and tangential contact forces during manipulation and their impact on grasping has been widely investigated in the literature, as Catie said earlier. However, contact mechanics occurring on the finger pad during dynamic touch has also been less widely researched. The authors intended to fill in that gap in the literature by centering their study on the psychophysical assessment of the human perception of decreasing and increasing modulation of the normal force in natural and low friction conditions. Tangential and normal forces are shown to be essential in rendering more complex shapes, such as bumps and holes. In general, a better understanding of the changes in normal and tangential forces, as well as the direction of these changes and their intensity on the finger pad, and how humans perceive this dynamic exploration, could help improve the design of tasks requiring haptic feedback in applications such as virtual manipulation, delicate teleoperation, robot-assisted surgery, and others. In these applications, understanding how normal force feedback affects users will help generate devices that adapt to their natural grasping and touch.
The experiment was carried out as follows. A 4-axis Scara Denso robot end effector was positioned beneath a static human finger, as demonstrated on the right. The human finger was couched inside a holder with a 20-degree tilt. The robot end effector slid along the finger at a speed of 2.0 centimeters per second and varied the normal force from the constant 1 Newton condition to plus or minus 0.1 newtons to 0.4 newtons in steps of 0.1 newtons. For example, the maximum force applied was 1.4 newtons, and the minimum force applied was 0.6 newtons. There were 3 conditions: normal force increase, normal force decrease, and normal force kept constant as a catch trial. 2 types of data were collected. The first, tangential and normal force data over time, was recorded between the finger and the sliding platform using the ATI Mini 40 load cell. The second type of data was verbal answers from participants. All subjects were asked 2 questions in a force choice format. Was there a change in normal force during 2 different time intervals? If yes, in what direction? This study was repeated 7 months later with the second condition of applying talcum powder to the subject's finger in order to affect the friction component. There were 10 right-handed healthy volunteers, 2 females, 8 males, with a median age of 31.5 years.
As shown in the top figure, this paper found that a linear relationship exists between changes in normal force and changes in tangential force holds across both conditions, which were the finger pad with talcum powder applied and the finger pad without talcum powder applied. As shown in the bottom figure, when the robot was commanded to decrease the normal force, it was found that the addition of the talcum powder had a statistically significant effect. However, when the robot was commanded to increase the normal force, it was found that the addition of the talcum powder did not have a statistically significant effect. They also found that participants were only able to identify the direction of the change in force at an above chance probability for only the largest changes in force of 0.4 newtons, even though the fingertip should be able to perceive changes in force as low as 0.06 newtons.
The researchers determined that normal force is the main tactile cue that participants used to detect changes in the perceived force overall. The researchers were able to discern this by checking the just noticeable difference for both tangential and normal forces with and without talcum powder. If participants relied on tangential forces to detect the force change interval, the tangential force threshold would have stayed constant or become larger in both the increasing and decreasing conditions for normal force. However, this behavior was not observed. As a result, the researchers were able to conclude that normal force seems to be the main tactile cue that humans use to detect force changes in this experiment. As Jasmin noted, participants performed poorly at the task of identifying in which direction the normal force had changed, as demonstrated by the plot on the right. The authors called this out as a surprising phenomenon because, as Jasmin also noted, humans are able to detect very small changes in normal force, up to increments as small as 0.06 newtons. More investigation is required to understand why participants had difficulty determining force direction changes, because they were able to accurately identify that a change in normal force at all had occurred.
As we can see in this new figure, the authors found that there was a slight improvement in detecting changes in normal force in the trials where the talcum powder was added to the finger pad. Some of the limitations and drawbacks the authors faced were that the stimulus rate of change was constrained by the mechanical properties of the robot arm. For instance, a 200 millisecond delay was needed in order for the robot to reach its change in normal force. This small delay could affect the realism of a haptic simulation using this platform. Another limitation was that the disturbance of frictional cues was fairly mild due to the addition of the talcum powder. Additionally, the normal force direction identification task could have been a separate experiment, rather than a second order task to the normal force change task. However, this does seem to be a step that the authors are considering next for their future work.